about Chapter 9. Chapter 9 is an important chapter, in fact, because let me tell you later on, for those of you who will be with the structural engineering major or aerospace engineering major, most likely you have to deal with moment of inertia very, very frequently. Again, that's the basic parameter to characterize how rigid that beam structure is. Because we talk about the bending rigidity, or in short, we call the flexural rigidity. That's basically E times I. E is a Young's modulus, or elastic modulus, or elastic stiffness, and I is the moment of inertia. So that's why that parameter is very important. It's much more important than centroid, in fact. Okay. So this chapter basically tells you a simple way to calculate the moment of inertia. Although in later courses, when you enter junior, like a 150, 151A for civil engineering students, we're going to continue to talk about moment of inertia. Okay, so this chapter is basically give you a simple idea to calculate a new concept, which is called the moment of inertia. So this one, in fact, is a moment of inertia, which by definition is integration y squared dA, which is the moment of inertia with respect to x-axis. Then, of course, correspondingly, if you want to talk about x squared times dA and integration, that is also called the moment of inertia with respect to y-axis. Okay? So these two are the fundamental definition of moments of inertia. Many times, you cannot integrate out by these two integral forms. So instead, you just need to know what is the moment of inertia with respect to the axis passing through, going through the centroid. Okay, and that is the special moment of inertia, typically we call Ix bar and Iy bar. So once we know these two basic moment of inertia, then we can claim, we can calculate the moment of inertia at any given axis we like, because of this important parallel axis theorem. From this parallel axis theorem, we can calculate the moment of inertia at any given axis you like, as long as you know the distance between this axis and another parallel axis passing through the centroid. So in other words, we do need to know D, and once we know D, we can easily calculate the area of this any geometry, because that's the mass concept. No matter what, the area is supposed to be the mass concept, right? And then we can use this equation to calculate out the moment of inertia with respect to this axis, which is equal to the moment of inertia with the special axis passing through the centroid, but parallel to this one, plus the area times d squared. And that is the theorem we called parallel axis theorem. With this one, we can calculate typically the moment of inertia of pretty much all the special cross-section area. For example, I briefly talk about this case, right? So typically in real engineering structures, we frequently use a wide flange. Sometimes we use the standard S, and sometimes we use a channel that's called C shape. Sometimes we call it angles. But no matter what, these are the simply combination of rectangular cross-section areas. So in other words, as long as we know the moment of inertia of this rectangular cross-section area, then we can apply the parallel theorem to calculate anything like this. And last time, I believe I spent some time to talk about this one. Okay? And some students ask me, do I need to worry about the curve here? You don't need to do that. You basically just assume this is the rectangular shape. There's another rectangular shape called a stem, and this is another rectangular shape. It's called a flange. Okay? So today, I'm going to talk about another example, just trying to show you how we can somehow take advantage of the charts typically we can get from this textbook, or typically we can get out. There's a lot of different categories in it's called the LRFD Design Handbook. LRFD stands for Load Resistance Factor Design, LRFD. Which is our kind of steel structure Bible in civil engineering, because basically it is very thick. There's more than 1,000 pages with all the information you get. If you want to become a structural engineer specializing in steel structures, that's really your Bible. You just have to look at it almost every day. Okay, so let me talk about this example and to see how we can calculate the moment of inertia. Okay, so we see this cross-section area something like this, which is the combination between two small geometry. One is a rectangle on top and glued with another, this is, you can call, it's not wide flange, it's called standard, I believe. It's called what, they should tell you somewhere. Okay, this W14/38. Okay, so the strength of W14/38 rolled steel beam is increased, is further, this one itself, this one, without talking about the top panel, this one itself is called standard, we'll call the W14/38 steel beam cross section, but this is further strengthened by putting additional top rectangular panel on top to increase the strength and also the rigidity as well. It's further increased by attaching a plate, a rectangular plate on the top to his upper flange, this one. Okay, so now we need to calculate the moment of inertia and the radius of gyration, which I'm going to give you some kind of definition. This is, once you know the moment of inertia, you can calculate the equivalent gyration radius. Okay, with respect to an axis which is parallel to the plate, that's mean parallel to the plate, but passes through a centroid of the section. The centroid of this whole section, not the centroid of this lower part. Okay, so then basically this one, we have the several things we have to figure out first. Okay, for example, what is that axis passing through the centroid? We were not given directly. You say, well, this point, this one, but we didn't give you from here to here is what? Or from here to here is what? We don't know it. Okay, and definitely the centroid of this whole structure is not the center point of this lower part. It's not here. You have to consider this part. So that's why we have to go over what we had in chapter 5 to have this problem completely solved. Okay? First of all, I would like to talk about this. If they gave you a certain designation, for example, you call the beam structure with a W something by something, then you just need to go back to look at your textbook. And I copied this chart for you. So if you are given with the cross-section with W14/38, then what you need to do is to go back to look at this chart first to see if there is a designation having W14/38. We do have one. See here, W14/38. I want to make sure it's correct, right? Yes. So, but just in case you couldn't find this one, definitely you can find one from the handbook. Okay, but of course we are relying on this textbook, so definitely we need to choose something from this textbook. The designation for W14/38, so that means if you're having this kind of shape, instead of calculating the moment of inertia by yourself, which is a combination of these three rectangular shape, you can take advantage of the result directly from the book. So in other words, for this W14/38, in fact, we know everything. We know the area of this cross-section, which is 11.2, is given here. And we also, if you want to know the specific geometry we're given, we don't need to use this one. However, we do need to know this is I bar, which is the moment of inertia passing through its own centroid, which is 355, right? And also the moment of inertia with respect to y-axis, that means this one, which is 26.7. Okay, and this K are something else we want to talk about, we didn't introduce. Okay, so in other words, going back to this example, we already know the moment of inertia of this one. Okay, so we can calculate the local moment of inertia of this one directly, and we also know the moment of inertia on the top panel, rectangular panel. So now it is our job to combine these two, localize the moment of inertia together by using the superposition rule. Okay, so first of all, we need to first calculate the centroid. So with this given cross-section geometry, Okay, we need to locate that point C, which is the centroid of this whole structure. By the way, you may say, how do we know this one? So either they already gave you all the geometries, or you can find out from the chart. For example, for this one, W14/38, you have a 14.1, 6.77. So that's why I have a 6.77. From here to here is 14.1. Easily, you can use this number directly, or you can get it from the chart. But this, on top of this one, you have a thin plate. The width is 9 inch, and then the thickness is the 3/4 inch. Okay, so first step, we need to identify the centroid of this overall structure. And we need to go back to look at chapter 5. How are we going to calculate the centroid of a relative complex structure? Okay, again, we're using superpositions. So this one should be split into two simplified structure. One is the rectangular geometry on the top, and the other one is typically W14/38. Okay, and in order to calculate the overall x bar, y bar, which are related with the centroid, what we're going to do is to make a chart. So the first column, we can write down the two components. The top one is called the plate, or you can call rectangular shape. The bottom one is called the W14/38, where you give whatever name you like, called the beam section, for example. Okay, followed by another column is what we call A, which is area. Okay, so just in case some of you forget whatever, you can go back to look at chapter 5 slides. So this is a column to write down the area. What is the area of this plate? And that's very simple. That's going to be 3/4 times 9. So 3/4 times 9 is 6.75. And the unit is inch squared, because we have inch by inch. Okay, so that's simple enough. What is the area for the second one? Well, the area of the second one is a little bit difficult if you really want to calculate. But again, I was telling you, you can take advantage of the result we got here. They gave you the area directly, 11.2. So that's why you just write down 11.2 directly. Okay, any questions? All right, so that's the easy part, right? And by the way, both are positive, because this time it's not something we subtract. If we are doing something subtract, then you need to put additional negative sign in front of the area, as basically we did in chapter 5. But this one, you just simply add them together, then that's perfectly fine. Now, the next column, we're going to talk about y bar. You may say, why not x bar? Well, we'll talk about x bar if you really like, okay? Because x bar is very simple to identify. So let's talk about y bar. Y bar, what is a y bar? We need to first figure out what is the coordinate system for this x bar, y bar. They forgot to plot the coordinate system for this one, but let's take advantage of this one, the same thing. For whatever, maybe this is referred to this one, in fact. Okay, so this is the original picture, but this is the picture we call the superposition. So first of all, we are going to set up the horizontal axis called x bar, x, and then the vertical is called y. The original point is the center of this lower part. Okay, so this lower part. And the centroid of the whole structure is here. That's what we call x bar. So we need to identify this C. So that's why from this C to O is what we call y bar, right? Because it's in the vertical direction. You may say, what is x bar? Well, due to symmetry, x bar has to be equal to 0. So that's why we don't list x bar here, because it's going to be finally equal to 0 for the global one. That's why we only want to have y bar. Now, for each component, for the plate, right? For the plate. So then what is y bar? With corresponding to this coordinate system, original point here, y bar for this small part, that's from the center to here. So the total from here to the top, from here to here is 7.05, right? So let's say from here to here is called the 7 point, this is divided by 2, in other way, right? 7.05. And then half of the thickness. The thickness is 3 inch. 3 inch divided 3/4 inch. 3/4 inch divided by 2, that's a 3/8. So 3/8 plus 7.05, that should be 7.425. Okay? Any questions? That should be simple geometry, right? Again, this number is obtained based on from O to this, the bounding point. That is the 7.05 plus half of this small height, which is 3a. And it should be 7.425. And that is y bar for this grid area. That's why you put it here, 7.425. What is the y bar for the second part, which is the W14 by 38? Well, because you set up the x and y corresponding to the center of this lower part, then obviously y bar is the original point. That's equal 0. Okay? That's why you put 0 here. Any questions? Okay, so once we got y bar for each component, then we are going to have y bar times a. So then this one times this equals this one. So second row, 0 times anything equals 0. And then you can add all a's together. Summation of a equals this, and summation of this one equals this. Then look at the composite rule, right, in chapter 5. So the summation of this divided by this, that's equal to the capital y bar. So capital y bar is the centroid, y component of this overall geometry cross-section. Okay? So you just put those numbers here, divided by 17.95, you get a 2.792. So this is y bar for the global cross-section. For example here, then from here to here, that should be 2.792 inch. Any questions? So again, all these slides, materials we're talking about, are based on chapter 5 principles, in fact, right? Because there's only first part to identify the centroid of this global cross-section. But once we identify so-called y bar, then we are going to move to the next to calculate the moment of inertia with respect to x-axis and later on with respect to y-axis. So again, one comment down to say, you may say, why are we only calculating y bars? Why we are not calculating capital X bars? The reason is the capital X bar for this structure equal to 0. Okay? Question?
How is the y bar being section 0?
You mean this one?
Yes.
Okay. Okay, going back to look at this picture. Keep in mind this second row, I'm talking of the local y bar, that's called the lowercase y bar. The lowercase y bar with respect to the second geometry with this W14 by 38. Now, for this one, we are picking x and y passing through the centroid or the center point of this second part. Then let me ask you, this O, point O, this point O is the centroid for the W14 by 38. If this original point is also the central point, then what is the local x bar, what is the local y bar for that second structure? That's 0, 0. So that's why this is equal to 0. Any other questions? Okay. So finally, we get this y bar calculated through this way. One comment I just mentioned, the capital X bar. For those of you who are supposed to think about what is the capital X bar. So again, I'm telling you, the capital X bar equal to 0. Okay? It's not something we don't want to use. It's something you can easily find out due to symmetry, because this is the capital, this point, right? This point, the global centroid. The global centroid based on this coordinate system, x, y, from C to O is called the capital Y bar. But let me ask you, what is the x components of this point C? What is the x component of point C? That's x bar, and that's equal to 0, because it passes through y-axis. Okay? You have another? Anybody have other questions? Okay, so this is the first step. We identified the centroid of this global structure. Now let's move to the next one, which is to calculate the moment of inertia. Okay, so there are two moments of inertia. One is called the moment of inertia with respect to x-axis, and one is called the moment of inertia with y-axis. Now let's go back to look at what's the original question we were asked. We need to determine the moment of inertia, I forgot about the second one later, with respect to the axis. This is the axis, okay, defined as parallel to the plate and pass through the centroid of the global section. This is the section for the whole thing, not for the second part. So in other words, we are calculating the moment of inertia, the moment of inertia with respect to this x prime axis. Do you accept this? We are not going to calculate the moment of inertia with respect to x-axis. Why? Because the question asks us to calculate the moment of inertia with respect to an axis which is passing through the global centroid. This is the global centroid. That's why it's called x prime. It's not this one. Okay? So our final goal is to calculate this one with the moment of inertia with respect to x prime. But in order for us to calculate I x prime, we do need to calculate the local moment of inertia with respect to each small area and add them together. So that's why, first of all, we want to calculate the, let me see. So we need to split this problem into two parts. One is the moment of inertia for this second part, I believe, or the first part. This one is the moment of inertia with respect to the second part. This one, W14/38, with respect to this x prime. And then we need to calculate the moment of inertia of this one with respect to the same x prime. Once we are done with these two, whatever number we got, we're going to add them together, and that is our final answer, which is the moment of inertia with respect to this x prime for the entire structure. So again, this plus this is called the superposition. Okay? So now let's do it one by one. So let's first calculate moment of inertia with respect to x prime based on this second component. We call W14/38. Okay, forget about this top rectangular shape first. Okay? And obviously we don't know equal to what. Because if you look at this local W14/38, the moment of inertia is the x prime, we have no idea. But we know the moment of inertia of this second part with respect to this local x-axis. Because that's, this point O is a centroid for the second part. Okay? This is a centroid for the whole thing. But this point O is a centroid for the second part. So then what is the moment of inertia corresponding to x-axis passing through the local centroid, the second part? That is W14/38, this one, x. This is the local centroid. What is that? 355? Okay, so I'm sorry, it's 385. Double check. My eyes are not that good anymore. 385, okay, and make sure the unit is inch horsepower. So this is the number we got from the previous chart. Okay, number one. Number two, we need to use the parallel axis theorem to transfer this one to this. Again, what is this? This is the moment of inertia of the second structure with respect to x prime. We know the moment of inertia with respect to this one, then we need to add AD squared. AD squared. What is A? A is the area of this second part, which is W14/38. What is the area of this one? 6.75. So we put 6, wait, I'm sorry, not this one. This one, the second part, 11.2, okay? So that's why we put 11.2, that's A, times D squared. What is a D? D is the distance between these two parallel axes. Okay, we just calculate from here to here. That is our capital Y bar, which is 2.792. So then 2.792 squared. So this, add them together, which is equal to 470 something. This one is the moment of inertia with respect to x prime for the second part only, for this part, W14/38. Any questions? Okay, I hope I'm not confusing you, but you really have to do it step by step. Otherwise, you may forget what you were doing before. So, once we get this one, we recognize this is part of the moment of inertia for the whole thing. We leave it there. Now we move to next one, which is this. we have a rectangular cross-section area. What is the moment of inertia of this small rectangle? Again, with respect to x prime. Okay? Which is equal to, again, the moment of inertia with its local centroid axis. The local centroid axis is passing through the center of this one here. This is 1/12. 9, this is 9 times 3 inch, 3/4 inch, okay, because it's thickness. This is called B, this is called H, okay? So 1/12, 9 times 3/4 cube. You may say, what is the formula we're talking about? Well, just in case you forget, I'm going back to show you this. And this is the only one I'm asking you to memorize, okay? So I'm asking you to memorize only these two. Nothing else for this chapter. But it doesn't mean I'm going to ask you something else. I'm asking you something else definitely based on these two equations. So 1/12 BHQ. BHQ, right? BHQ. Okay? If you're talking about with the y-axis, that's 1/12 B cubed H. Because once you know these, you can pretty much deal with almost anything you like to do, in fact. Okay? And you go back to look at those 4 questions you are going to turn in on this Friday. These are all related with this one. Okay. Going back to this one. So the local moment of inertia with respect to the local centroid of this rectangular shape is 1/12 BHQ. This is the B, which is 9. H is 3/4, and then Q. So this part is in this local moment of inertia. And then plus, again, using the parallel theorem, plus AD squared. Again, what is A? A is the area. That's easy enough, right? So 9 times 3/4. 9 times 3/4 is 6.75. That's A. Then what's the D? What is the D? D is the distance between these two parallel axes. So this is one axis, this is another one, and that's D. They already indicate this is D. So what is the D? So this D is basically, okay, so there's many ways you can identify D anyway. So maybe one way I can say is from here to here, okay, and then minus this part. So 7.425 is from here to here, and then minus y bar. So 7.425 minus 2.792. And that's D. And don't forget with the square here. And then you punch your calculator, you get another number, 145. And the 145 inch to the 4th power is the second moment of inertia with respect to x prime based on this rectangular cross-section. That's the second part. So once we know the first part, we know the second part, now we use a superposition rule to simply add them together. Why can we add these two numbers together from physical point of view? Because both are moment of inertia, and more importantly, you can add them together because each of them is corresponding to the same coordinate system, which is called x prime. This one is corresponding to x prime. This one is corresponding to x prime. That's why you can add them together. For anything you use a superposition, whether in chapter 5 or in chapter 9, this chapter, you need to make sure any number you calculated should be, if you want to add them together, you must make sure they are talking about the same language. In other words, they have the same coordinate system. So that's why this one is x prime. This one is also x prime. So they can communicate directly. Okay, and that's a requirement for any of you who want to use the superposition method. Okay, so finally you can add them together, and that is called I, the moment of inertia of the whole structure. Okay, for the whole structure with respect to x prime axis. And this x prime axis is passing through the centroid of this global cross section. Any questions? Okay, one more thing. We are asked to calculate the radius of gyration with respect to this moment of inertia. So I just want to give you the definition. This is the definition of the radius of gyration, because I think the homework question probably asks you to calculate the same thing. But don't worry about that. As long as you can calculate moment of inertia, you need to divide it by the cross-section area and then take the square root. And that is what we call gyration of radius of gyration. Any questions? Okay. So this is another example just to typically show you, just in case, if you were given with a specific wide flange or standard or channel or something, again, you can use a superposition, but obviously you can take advantage of this chart. You may say, well, I'm not asking you to memorize this because there's no way you can memorize those. Then the simple question is, are we going to have some kind of question in the final asking you to do something like this, the combination? Well, think about it. I can define a certain, like S10 by 25 or W8 by 31, and I gave you that chart, right? Then you still need to do it. Okay, I'm not asking you to memorize these numbers because that's not the thing you're supposed to memorize, because you're supposed to get it from the handbook. But of course, the final exam is a closed book, right? There's no way you can look at the handbook, but I can give you some numbers if I need it. Okay, so that's why I'm pretty sure typically for those structure, you just need to memorize this. But it doesn't mean you can only calculate this one. You can calculate many other things using what we call the parallel axis theorem.